Is everybody having a good conference? That's great to hear. So we're going to talk a little bit today about template techniques, and the way I explain this to people is this is not 101 templates. We're not going to go over the syntax of basic templates, but it's not advanced either. We're going to just basically touch on some metaprogramming stuff. So this is the intermediate stuff. This is templates 201. We assume you know some stuff about templates. We're going to have a little exercise in just a second to verify that, and then we're going to more or less talk about what we do once we've created our first template. I want to introduce myself. My name's Jon Kalb, and someone told me, I was talking in the hallway yesterday, and they said, "Oh, I didn't know you do training." I said, "Oh my gosh, that's my livelihood. Yes, I do training." How many of you think your life would be better if you knew C++ a little better? How many of you think your life would be better if your coworkers knew C++ a little better? All right, I'm seeing a lot of hands. Send me some email. We'll make that happen. All right? Okay. All right. So for reason of time, I'm going to skip one of the sections here because this is actually from kind of a larger training expectation. But I will put those slides on the slides that I give you. So if you're interested in that, you can go through that on your own. But the first thing we're going to do, and I may also not have time to go through the end. We'll see if we get there. The first thing I'm going to do is we're going to implement the simplest template function. How many of you implemented a template function before? All right. For those of you who haven't, you're going to be able to update LinkedIn and say, "I've now implemented a template function," because that's what we're going to do right now. So we're going to create a template function from scratch. But don't get too excited. It's just the simplest function in the world. We're just going to add two things. Okay? But you're going to write it. So how's it going to start? Okay. We're going to say template and then some class and some arbitrary identifier, but by tradition we say T, right? Okay. Now we have to get to the function signature. And what do we want to do for that? Well, let's, all right, that would be great, but we're not going to do that. Okay, so, but I've already given you the name of the function. So what is this, what do we want to do for the signature here? T, add, right? That's right. T, add, TA, TB, all right? Okay, now we have to do the hard part. Now we actually have to implement it. So what is the implementation going to be? Oh, well, maybe that's not as hard as I thought it was going to be. I don't think this is quite ready to ship as a professional library yet. What's the problem with this? Oh, I guess I just told you. What's the problem with this? We don't know what T is, and T might be very expensive to copy. Do we need to copy in order to add? No. So how do we avoid the copy? Right, let's do it by reference, okay? All right, okay, great. We have now implemented our template function from scratch, and you can update your LinkedIn account and add this as a skill. I want to make one little change before we go on. We have indicated that we're adding two of the same type, right? It's two different T's. What if we wanted to add two different types, right? What would we have to introduce now? What do we have to have? Another type, and by tradition, we'd usually call that U. All right? So if we did that, we would do this, right? Okay? Everybody good with that? What's the matter? Wait. Don't get too far ahead, Peter. I'm going to have to talk to you. All right. So what's the problem here? It's the return type, right? We're assuming that it's T. But it may not be T, could be U, right? In fact, those are the only two things it can be. It's either going to be a T or a U, right? No. In fact, it pretty much could be anything. You know, the standard says that if you have two items that are smaller than an int, if you add two items that are the same, you'll get the same. So you add two chars, you get a char. But if you add a char and a short, it promotes to int and adds them together. So the answer you would get for adding a char and a short is an int. So it is quite possible to take any two arbitrary types and add them together and get yet another type. So not thinking at all about C++ or code in words, what is it that we want to return? whatever happens when you add together whatever A and B are, or whatever these T and the U are when you add them together. So what we want to say is that we want to return decal type of T plus U, right? Okay, we good? What's the matter? Right. So decal type requires an expression, and T and U are not, they're not values, they are types, and so we can't add the types together. So what is it that we need to say instead of T plus U? What do we need to say? Well, we'll get there. What? A plus B, right. So we make that A plus B. Okay, now we're good, right? What's the problem? I've defined them. I define them right after I use them. That's what the compiler wants, right? Okay, so this isn't going to work. What do we need to do now? Right, trailing return type. Okay, so I've gone through this, and the reason I did this is because I wanted to demonstrate that even the simplest template function in the world, we couldn't implement it until we had C++ 11, because we've used not one but two features of C++ 11, the trailing return type and decal type, both of which were introduced in C++ 11. So classic C++, we couldn't really do templates at all. Well, actually, we did lots of templates in classic C++, but there were some really simple things that prevented us from being able to do what we wanted to do. This, of course, is C++ 11. In C++ 14, now we have another tool. What would that be, Peter? Right, we can use auto to detect what the return type is, and so in C++ 11, it's even simpler, right? Or 14, it's even simpler, okay? All right, so that's our simplest template function. We're going to skip CRTP and jump right into type traits, which is kind of the basics of how we get to metaprogramming. So type traits are things that we can query at compile time, obviously not of runtime values, but of type attributes that we can know at compile time and then use those to make decisions about what we want to do. So how could we determine if a template type is an int? So the way we do this is we actually create a template, and the template is going to be, in this case, we're going to call it isInt. And most types are not ints, so our default behavior is going to be that for isInt, we're going to have declared a static bool const that is false, and that's most of the time. And then we're going to specialize this for the situation where it is an int, and for that one we'll say true. Okay? All right, and this is how we might use this. We might say isInt of float, and obviously that's going to be false, and isInt of int is true. Now, of course, this is very straightforward, and you say, well, this doesn't make any sense. In a more complicated situation, it might be isInt of t or isInt of u. It's not obvious whether it's an int or not. But this is the building block of how we do compile time attribute testing. So there is a now convention that we will use underbar v to, rather than having to say something : value as our answer, we'll use underbar v, which is a template that goes ahead and gets the value of our type. All right, so how would we determine if two types are the same? Using the same kind of technique that we just did, what we'll do is we'll have a primary template is same, which is just false, because most of the time it is false. And then in the situation where we have the same type, so we'll specialize it for where instead of having t and u, we have two t's, and we specialize it in that case and say it's true. And then we're going to follow the convention and say is same v is it's just a template to get our value for us. Okay? And so we can do the same kind of testing here. We can say is same float an int or is same int an int. Okay? And again, this would be a little bit more interesting if this was in the middle of a template and we didn't know what types we're using. So we could say is same t and u, or is same some different types, which we don't know what they are. All right, so those are type traits. Now we're going to talk about type functions. So a type function is a function that takes types as the parameter and returns another type. That's a type function. And type functions are not supported directly as first-class things in C++, but we can emulate those very easily, again, using templates. And again, we have a convention, and the convention is that the type, because we don't actually have type functions, we're not actually going to return a type. So what we're going to do instead is we're going to make a member type alias of whatever the type is that we want to return. So, so we can create that, and again, we have a convention that says whatever the type function is, instead of underbar v for a type trait, we use underbar t for a type function. So here we're going to have a function that removes const. So we call it remove const, and in the general case, we'll just return the type, because in the general case, it won't be const. And then we'll specialize it for the situation where t is const, and then we'll just, again, return t, but that's because the pattern matching has pulled const out of the t. Okay? So this is a very simple type function. Now we'll define our underbar t version of that, which is simply to get the type defined member that we've defined there. Okay? So now we can say is same int and remove const of int's const, or is same int and remove const of int const, or excuse me, int const, is that the same as removing the const? And so the first one is true because the two ints are the same, and the second one is not true because we removed the const, and so they're not the same anymore. Okay? All right. So now we're going to talk about all the traits. Well, we're actually not going to go in great depth here. I just want to show you these are the traits that are defined for us in the standard, so that we don't actually have to write our own remove const and all these kinds of things. These are done for us. And some of these things really do need some kind of magic between the library and the compiler, because some of these things are hard for us to actually implement. But the compiler can tell the library, or the library can somehow ask the compiler, is this in fact a union or something like that? So all these things are available to us, a whole bunch of different characteristics, and the way to find this, of course, cppreference.com. There's one particular one I want to point out, enable if. We're going to talk a little bit more in depth when we start talking about our next step, which is compile time conditionals. So there's a number of different ways that we can do compile time conditionals. One of them is using tag dispatch. So in the standard, there's something called std distance, and distance is designed, you pass in two iterators, and it determines how far away these are. And the assumption is these are pointing into the same range, right? So we need to know how far that is. Now, what's the complexity of this function? Depends on what? The type of iterator. What is the best case I could imagine here? Okay, if I have random access iterators, then what's the complexity? Constant time. What if I don't have random access iterators? Then it's going to be linear, right? Now, what I would like to do is, and this is why I have this nice function, I want to have a particular thing I call, which gives me the correct answer, but I also want it to be efficient, so that means I actually have to do it two different ways. I do it one way if it's random access, and another way if it's linear. So that's actually pretty easy to implement these things. I can either do it in a loop, or I can just use subtraction. Okay, that's pretty easy. But what's the problem with this? Is this going to compile? What's the problem with this? Right, I just redefined distance, right? So what I need to do is somehow say, well, use this one in this case, but this one in this other case. So what we do is we use something called tag dispatching. And the idea is that we're going to add a tag to the signature of these two functions. So the compiler at compile time will dispatch to the right function depending on the tag. And the tag we're going to use here is std input iterator or std random access iterator. These tags are already defined in the standard. Now, if we were trying to do something like this, we could define our own tags, whatever type we want. But these are handy for us. So the idea is now we have two different versions of this function. They're overloaded on the same name. It's great for the callers, but we don't want the callers to have to pass in the iterator tag. We would like that to be determinable at compile time, which it should be. And so what we do is we create another function, another overload, and this overload doesn't have a tag at all. And so that's the one we expect the users to call. And then we just turn around and call the overload again, but now we figure out what the type tag is by asking the iterator category. This is one of our type traits. Okay? And so this dispatch then is done at compile time. The compiler is just picking the right function to call, and then we get the best implementation for performance, but it's all rolled up. Okay? All right. So that's our tag dispatch approach, and this is a classic approach that's used all over the standard library and in lots and lots of implementations. There's another approach which uses compile time conditional overloading, and in this situation what I have is I want to write a function called copy array, and I'm going to give it 2 arrays, and they have to be the same size, and then what we're going to do is we're just going to copy from the source to the end, or excuse me, from the source to the destination. And by calling standard copy, of course it's possible that standard copy has some great optimizations. In fact, it's probably likely that it does. But we'll assume for a moment that standard copy isn't optimized, and it's simply going to do the naive, I'm going to copy one item at a time. And that's going to work great for us in a lot of situations. But what if, for example, what we wanted to copy was integers? Is copying one integer at a time, is that going to be what we want to do? We could do better performance-wise by doing what? We just call memcopy, right? So that'd be great. So what we could do is we could just say, okay, I want to specialize this for the case where instead of having t, I have int. And I'll just call memcopy. Okay? Great. The problem with that, though, is what if it's a float? And in fact, now you begin to realize, well, there's lots of types that actually memcopy would be better. And so we have to add a whole bunch of overloads, and we're likely to overlook something, and it's likely to be a mess and be hard to maintain. And that's not the road we want to go down. What do we do when we want to write code to handle lots of different types? That's what templates are for. So what we can do is we can just say, oh, I want to have an array, a copy array for t, and it does memcopy, and it's not going to be restricted down to ints. That's going to work with floats. It's going to work for doubles. So that solves my problem, right? What's the problem now? What's the problem with adding this overload? What's that? It's not an overload, right? It's a redefinition, right? It's a redefinition. It's got the exact same signature as our primary template up there. And so that's not going to work for us. So what we'd like to do is somehow say, well, if it's memcopy safe, then we're going to use, if it's not memcopy safe, we're going to use standard copy. But if it is memcopy safe, we're going to use memcopy. That's what we would like to somehow say. And there's actually a term for this in the standard. Sorry, I get ahead of myself. So what we're going to do is we could use tag dispatch here. We could actually create a copy array with a third parameter, and in one case it would be a memcopy safe parameter. In one case it would be memcopy unsafe parameter. We could do that. That would work fine. But instead, just to try it out, we're going to use enable if on this. So the memcopy safe is in the standard is trivially copyable. So what we're going to do here is we're going to say that copy array, both versions now, the return type is actually enable if either not trivially copyable or is trivially copyable, and void. So enable if t takes 2 parameters. The first is a compile time constant expression. Of course, we would not surprised that it has to be at compile time, right? That compile time constant expression. And the second is the type that is used. In other words, this enable if is going to return a type, and the type that it's going to return is void if that expression is true. And the idea here is that we're going to enable if the first expression if it's not trivially copyable, and then we're going to enable the second one if it is trivially copyable. So it turns out that there's actually, for enable if, there's a default parameter which happens to be void, so I don't actually need that. I could write it a little bit simpler here. A better name for enable if would probably be ignore unless, because templates are inherently enabled. We don't actually have to enable them in practice. This is a special magical way to essentially say, don't enable this or disable this. And so that's actually probably a better name for it. You could think of enable this as ignore unless, because that's what's really happening here, is that we have created 2 overloads which the compiler wouldn't be able to pick from, except that in one case, if the item is not trivially copyable, that's going to be ignored unless it's not trivially copyable, and the other one will be ignored unless it is trivially copyable. All right, so if the expression evaluates to false, notice we've told it what the type is if the expression evaluates to true. And in this case, both of them become void if it's true. But if it's false, then it's disabled by SFNA. And what that means is SFNA is an acronym for substitution failure is not an error. So what's happening is that when we write code that calls copy array, the compiler makes an overload set. So an overload set is the set of candidate functions that might be considered. So first, the compiler looks for everything that is, and there's some complicated rules about the scoping and all that stuff, but it makes a set of all of the things that are called copy array. And then it has to go through that set and say, is this a viable candidate? It's a candidate because it has the right name. But then it will look at things like, well, how many parameters does it take? Because if I'm calling copy array and I'm passing 2 parameters, the compiler finds a copy array that only takes 1, then it can ignore that one. But the other thing it can ignore is when the compiler evaluates the candidates, it tries to say, well, is this a viable candidate by substituting what the template types would be? And it is possible that when substituting the template types, it won't find an answer. It will be an error. And instead of refusing to compile, saying, wait a minute, there's an error here. There is no such type you told me to calculate. Instead, what it does, it says, oh, for this particular template, I have a substitution error. A substitution failure. And instead of failing to compile, what I'm going to do instead, I'll just ignore this particular template. Substitution failure means ignore the template. And that's what's going on here. So let's think about how we would actually enable or implement this enable if. So in the true case, it's pretty simple. Because remember, we said in the true case, we're going to return whatever the second parameter type was, or the second parameter type. So here we're saying in the forward declaration, it's just an incomplete type. We just say there's some struct called enable if, not giving you a definition for it at this point. And then we say I want to specialize for the situation where the first parameter, that Boolean expression, if it's true. If the Boolean expression is true, then the type we want to return is just the second type. That's very simple. Now comes the tricky part. How do we implement the false case? We don't. That's kind of the whole point, is we don't want this to work in the false case. We want the compiler to say, I'm just going to ignore this. I'm going to disable this function. And so we just don't implement the false case. So when the compiler is trying to figure out, is this template a viable candidate, it does the substitution. If the substitution succeeds, it uses the type that we've said, the type equal t. That's what the entire enable if just resolves to the second type you gave it. But if the expression is false, then the compiler can't figure out what type to use, and so that's a substitution failure. There's no type available. There's no definition. In the false case, there's no definition of what type is. So it fails, and therefore it ignores or SFNAs out the template. So we don't have to implement it at all. So now what I did was I enable if the return type. And that's perfectly viable. That works great. But as a style issue, people are starting to say, well, I'd like my signature to be a little more readable for users. So one popular thing is to add a new parameter which has a default value. And in fact, is never used at all. It's only used to determine what the signature is. And if you put the enable if on this parameter, then it's easier to read the signature. I can see what the return type is. Oh, the return type's void. I see all the parameters. And then I have this weird last value that's enable if. And so I don't have to worry about it at all. It has a default value, and I don't pass it. It just makes it a little bit easier to read. Again, you can actually do the enable if on any type in the signature. It can't be in the body, because, of course, the compiler is only looking at the signature to figure out if this overload is a viable overload. Okay? So just as a style thing, I think people are using return types less and using something like this to make it a little easier to read and understand the code. All right. So there's another way that we do compile time conditionals, and that is with const expert conditional. So until C++17, the granularity of our overloads was always at the function level. Type dispatch would dispatch to a particular function. And SFNA is SFNAing away particular functions. So everything, the granularity of that was always at the function level. But in C++17, there's a new feature. The standard calls it const expert if. but it is spelled if const expr, because the standard thinks that C++ is not complicated enough, so we got to come up with weird names for things, right? So what we have, something that's very obviously should be called if const expr, but the standard calls it const expr if. Okay, so the way this works is pretty simple. We have an if inside our body, so we don't have to worry about any kind of sphenae, we don't have to worry about any kind of dispatch. We just have one function. Here's our function, copy array, and inside the body we can say if const expr, and this if const expr, of course, we've been talking about what's being done at compile time. So the magic of if const expr is that it's not evaluating that at runtime, it's evaluating that at compile time. So the if const expr requires a compile time constant Boolean. Okay? And in this case, our compile time constant Boolean is this trivially copyable? If it is, we go down one branch, we do the mem copy, else we go down the other branch. And as I said, this is never evaluated at runtime. When the compiler is generating the code, it's going to, remember this is a template, so it's going to, at compile time, generate code that for whatever the type T is, it's either trivially copyable or not, and it generates one or the other. And in fact, what's passed in has to be compile time, Boolean constant, and the branches that are not taken, that is the statement, if it is const expr, then this else branch, if the const expr is true, then the else branch is discarded. If it's false, then the non-else branch is discarded. And those don't have to make semantic sense. They are discarded. They don't generate any code at all. Now, the compiler has to be able to parse these things. They have to make syntactic sense. Because if the compiler can't figure out, in the case of your else, you have else left brace, it has to know when it gets to right brace. So if you just pound on the keyboard and say, well, this branch is never taken, it's just going to throw it away. No, it has to parse. It has to make sense, but it doesn't have to be able to generate code. So if you had an else in there and you're calling a function and the function parameters just don't make sense at all, that's fine. That's fine. There's no such function that takes this set of parameters. That doesn't matter because the untaken branches are just discarded. They don't have to be able to generate code. All right. So I think const expr conditional has a lot of advantages over the function granularity. There are fewer functions to write, and every time we write a function, there's almost certainly some kind of boilerplate that's being duplicated. Anytime we duplicate something, it's likely that, or it's possible at least, that we have a copy and paste error. So it's easier if you just have fewer functions. Further, I think it's easier to read and understand what's going on. Even if you are familiar with tag dispatch, it's a little more confusing to look at tag dispatch and see what's going on than it is to just look at a single function which has this if const expr structure inside it. Right? So I think it's easier to read, easier to comprehend, and I would say a good deal easier to maintain because we have fewer functions. All right. So we're going to shift a little bit, and we're going to talk about policy classes. Policy classes were probably most made famous by Andrei Alexandrescu in modern C++ design. But the idea with a policy class is that when we are designing something, designing, of course, is making a bunch of decisions about something. That's what we're doing. We're making a bunch of decisions. And in some cases, the decisions are pretty straightforward. If I'm making a class and I know this particular type, the point of this type is to save memory, I'll make that decision at every point. Which is the path that saves me memory? Usually we look at performance, and so we look at performance. But sometimes we have situations where it's like, well, there's no particular performance, but users might prefer this or prefer this. And oftentimes in libraries, we make those decisions at runtime. We just pass a parameter in and say, do this, in this case, do that. But sometimes we would like to be able to do this at compile time, because perhaps one of our options, if we go down this path, we need to create some data members, which would take up memory, which if we don't go down that path, we don't want them at all. So we would like to make this decision sometimes at compile time. And the thing is, so what we're trying to do is we're trying to allow the user of the library rather than the author of the library to make the decision. We're allowing the library to be customizable. That's what we're trying to do, but we want that customization to happen at compile time, not at runtime. So the way we do this is that the library author, and by the way, this is driven by the library author. The library author has to specifically say, I would like this to be customizable. this particular design issue can be implemented either this way or this way, and I'm not going to make that decision for the user. The user will make that decision by instantiating my this type with a policy class. So in this case, let's say I'm creating a container, and my container has the indexing operator. And I have to decide when the user wants to index into the container, what kind of checking do we do? Right? This is an opportunity to bounds check. And as the implementer of my container, I can do it in a whole bunch of different ways, and different users might have different ideas about what's the best way to do it. Right? So what I've decided is that my container is going to be templated not just on T, which is the type of items being contained, but also on this thing called a checking policy. And the checking policy is the policy class. So when you instantiate my container, you say, I want my container of string with this checking policy. Well, what's the checking policy? Well, a checking policy is any type that happens to have a member that looks like this. So it needs to have a check bounds member, and I'm going to give you the lower bound and the upper bound, and I'm going to give you the value, and you as the user of the class can say what you want done in this case. What kinds of things could we do? What are viable options here? We might do nothing. That's the vector class, right? Vector class does no bounds checking at all. This is entirely on the caller to make sure that's correct. What else might we do? What? We could throw an exception. What else might we do? I think the author of this class didn't expect a policy to do that. Arguably, you could say, yeah, we're going to change the index to something that is viable. And then you have to worry about, well, what happens if it's an empty container, there's no viable. I don't know what we would do in that situation. All right. What else could we do? We've said we could throw, we could do nothing. Anything else? What's that? We could assert. Anything else? What? We could do a callback. Right. There's a few things we could do. Notice, as the author of this class, I could think about a few different obvious policies, and I could, in fact, implement those and give them to you as the user of the library and say, by the way, here's a bunch of policies. You can use them. But the real power of this is that, and you can also do whatever the heck you want. And that's what's nice about it, is a true customization point. So in this case, the provider could say, well, here's the do-nothing version, here's the assert version, here's the throwing version. These things are there. You could imagine also, oh, I want a version that just drops into the debugger right at that time. Whatever it is, just drop it in the debugger. Or log it, or there's any number of things you might want to do. And so the author of the library can give you a bunch of different policies, but you can make your own as long as the author of the library has documented what is required, and that's what we have, is here's this check bounds. So why couldn't we do this with a virtual function? Notice one of the things we could do is we could make the library itself a base class, which calls the overloaded function called checkbounds. That would work, right? And then you just derive from this and write what you want checkbounds to do. Why not do that? It's not cool. Well, that may be true, but why is it not cool? All right, so the issue is that if we do this at compile time, one of the options, in fact, what may be the most popular option, the do nothing option, completely compiles away. There is no overhead to do nothing. And I think to do nothing, no overhead is about the right amount of overhead, right? That's what it should, I can make that go away completely. But imagine I had done this using the virtual function. And so I derive from my base class, and I implement the virtual function to do nothing. It just immediately returns. Now what's going to happen when every time I actually do the index operator, what's going to happen? Well, the compiler doesn't know from looking at the base class that it's a do nothing operation. So it's going to have to do the dereference to get the vtable entry for the virtual function, and then it's going to have to call that virtual function. It's in most cases, virtual functions are not inlineable, right? So we have a significant amount of overhead for what may be the most popular option, to do nothing. And we've added this overhead. So that's the power of the policy class. It allows the author of a library to allow the user to make decisions about what the behavior should be and allow those decisions to be made at compile time. All right? Okay. So let's talk a little bit about perfect forwarding. So here is my... So here is the motivation for perfect forwarding. What is perfect forwarding about? So we sometimes have a layer of functionality that we want to add between two layers. So there's parameters passed down to us. We want to do something independent of what those parameters are, and then pass those parameters on down. So imagine I have created an application, and in my application, I use a particular library. And the question comes up, how much time do you spend in that library? Maybe it's a graphic library, maybe it's a networking library, something like this. How much time do I spend in that library? Is that an interesting question? You might conceivably be asked that question. So how could I answer that? Well, what I can do is I can create a timer class that has a static data member that keeps track of total elapsed time. And what I do is, when I instantiate the timer, the constructor calls now, finds out what the current time is. And then the destructor calls now and figures out what's the elapsed time in the lifetime of this particular instance of this type, and then adds that to the total accumulated time. Does that make sense? In other words, we have changed the question from how much time do we spend in this library to how long do these objects exist in total. And so all we need to do is we create the timer object right before we call the function. And then when the function returns, the timer object goes out of scope, the destructor is called, and we add the elapsed time spent in the library. Does everybody see how that would work? Does it make sense? Okay, that's great. We have a bit of an issue, though. I don't know about you. I have never worked with a library where none of the functions had parameters. Right? Functions are going to have parameters. Okay, so this function, we can say, by the way, in this case, we're cheating by using 14. I shouldn't say cheating, but we're taking the easy way out with the 14. We don't have to think about what the return value would be. But if we were not in 14, if we were using 11, we could say, oh, I'm returning the decal type of whatever calling f returns. Okay. But now we have this issue, what if we have a parameter? And so the question is, well, it's pretty straightforward. We just add a new template. Doesn't matter the type of the parameter. We add that, and we pass that in to the function when we call it, right? Straightforward, makes sense. But there's a bit of a problem here. What's that problem? What's that? Well, okay, eventually we'll have multiple parameters. We'll have to deal with that one too. But for right now, let's talk about the particular one. Somebody said, I think this is passed by value, right? Well, that's fine. That's going to work in a lot of situations. But we don't know what f is doing. And f might be modifying t. That might be what it does. And in this case, would that compile? Would that still work? Sure, because f can modify t. But what t is it modifying? It's modifying our copy. The caller's t is going to be copied and will not be modified. So that's a problem. So what we can do then is we could solve that by passing in a reference. Okay? Does that solve that problem? It also makes it more efficient because there's one less copy going on. So this is how we should do this, right? Is this gonna work? What's the problem now? What? It's possible that we're passing in a temporary, and if that's the case, then this isn't going to bind, right? Because the compiler will not allow us to bind a temporary to a non-const L-value reference. So we have that problem. So we could do this, right? So the issue is, we could write a bunch of different overloads to perhaps guess what all the situations are, but the problem with that is, one of the problems with that is it doesn't scale. And so the solution to this is something called a forwarding reference. And the magic of a forwarding reference is that it will bind to any type, And in fact, it's that reason that Scott Myers came up with the term a universal reference. Scott Myers coined this term universal reference, and members of the committee took some umbrage and said, wait a minute, C+11 created a new kind of reference, which is an R-value reference, and you're now going around and telling everybody there's this other thing as well called a universal reference. The committee said that's wrong. Should not do that. Scott argued, on the other hand, this is the best way to understand what this special weird thing is. Because the weird thing about what he was calling a universal reference, he said the interesting thing here is that it has the syntax of an R-value reference, but it is not safe to move from. Which, when we introduced R-value references, we said the reason we have R-value references is so that you can move from them. And then you turn around and say, well, there's this other kind of R-value reference that you can't move from. Scott says you have to make that, you have to distinguish that somehow. So he gave that a name and he called it a universal reference. And members on the standards committee objected pretty strenuously to that. And then, in the next version of the standard, they needed to be able to describe this situation where you have these references that can bind to L values or R values. And so the standards committee made up the term forwarding reference because they had already said universal references was a bad idea. I think Scott won the argument. So people call them universal references, people call them forwarding references. They're exactly the same thing. And what they are is something that syntactically looks like an R-value reference, but it is in the context of type deduction. And that type deduction context allows us to bind either to an R value or to an L value. So it always is an R value, but sometimes the R value is binding to an L value reference. And when you have references to references, we have special reference collapsing rules, and the reference collapsing rules say that the only time we get an R value reference when we collapse is if all of the references are R value references, because otherwise it's not safe to move from. So we don't want to get an R value reference if there's an L value reference in there. So in the type of deduction, we can deduce an L value reference and then have an R value reference to it, and that means it's an L value reference. So that's why the forwarding reference or the universal reference can bind to everything. And then we have this thing called std forward, which we can use to do the forwarding. So here we now are going to use this, what looks like an R value reference. But how do we know that that's not a normal R value reference? It's actually either a universal reference or a forwarding reference. How do we know that? Well, it's not because of the template. It's because T is being deduced. That's the reason. If it was a template, but we weren't deducing what T was, then it would still be just a regular R value reference. But the fact that T is being deduced, that type deduction, what that means is that when we deduce T, it can be anything, right? So one of the things it might be is it might be an L value reference. So we could be taking an R value reference to an L value reference, and that means that we end up with an R value reference. So we are binding both. And once you have this little t now is bound to something which it may be able to move from and may not be able to move from, that puts us in a weird situation. Because it's great that it binds to everything. It allows us to forward all types of things down. I don't have to make one function for the temporary case and one function for the non-temporary case, the L value case. I don't have to. I can write one function. But now the problem is, when I am forwarding this, do I forward it by passing it forward as an L value or as an R value? In other words, do I want to do an std move? And the answer is we do something called std forward. And std forward is a conditional call to std move. Forward takes this template parameter t, and remember t has been deduced to either be an L value or an R value. Excuse me. It's been deduced so that it may be an L value reference. Let's say that. So if t is an L value reference, then we don't want to move. So forward then evaluates to nothing. It's a do nothing operation. But in the case where that t is not an L value reference, then it says, oh, this is a temporary, and therefore I should be able to move it. And so std forward then turns around and calls std move. So it's a conditional call to move and allows us to forward. Okay? So this is magic. What I'm showing you right here, this is magic. Because what's happening is I am binding to any type of parameter and then efficiently passing it on, efficiently forwarding it. So in the temporary case, I'm moving it and in the L value case, it's not a temporary, then I'm copying it. So I'm doing the most efficient thing. I'm doing the most efficient thing, and I'm doing it with one function. I don't even have to do an if here. The conditional is inside the std forward. So my code allows me to focus on all I'm focusing on, which is everything except the forward. My code here, the important thing is that I'm creating a timer. Okay? All right, now we're going to get to the issue of what if there's more than one parameter, and this is where we use another feature from C++11, which is variadic template parameters. And in this case, that's what the ... is telling us. So class ... args is saying that this, unlike API function, args is not a template parameter. It is a template parameter pack. It is 0 or more template parameters of arbitrary type. And then in our function signature, we reverse the order and we say args ... And that unpacks that template parameter. And what that's saying is there's a parameter, a function parameter for each of those types, but it does it intelligently. It is not a simple text substitution. It looks at it intelligently, and the compiler realizes that you don't want the types of the args. What you want is R values of args, or R value references of args. And so it expands this not just as lowercase args being parameters to uppercase args, but lowercase args is actually a parameter to universal references or forwarding references of args. And then we reverse the ... after the args that says unpack lowercase args. But again, it unpacks it intelligently, so it is doing the forwarding of each individual type with std forward. So what this means is not only do we have an arbitrary number of functions that can be of arbitrary types, but each one is individually being std forwarded. So each one is either moved or copied as is appropriate. Okay? This is possible to do in classic C++. I think the Boost authors managed to do this. It's very, very challenging, but they didn't have variadic templates, but they were able to create functions that would work with any number of arguments up to infinity, where infinity is 12. Right? Obviously, lots and lots of macro magic and all sorts of stuff. It was all very advanced stuff. It was possible to do, but it required a lot of arcane magic. But with these two functions, variadic templates and forwarding references, we can now do perfect forwarding. So it's really easy for me to do something like I wanted to do, which is I want to time every function call. So every function in my library, I just wrap that function call in time call and then pass in the parameters, and they are perfectly forwarded into that function. And at the same time, I am collecting the total time spent in there. Okay? So this is how I can implement this, right? I will say perfect forwarding is not really perfect. There are a few failure cases, but those are really pretty obscure corner cases. But perfect forwarding is really a valuable tool. It is not the kind of thing that most people are going to write every day, but library authors are going to find it a really valuable way of being able to insert some kind of behavior where we have layers that we don't care about the data passing through. We want to be able to forward that data from a caller into a callee. So that's the perfect forwarding. All right, so the last thing we want to look at is viewing deduced types. So as we do template things, we often get into a situation where the compiler is deducing a type for us. And we may get a compile error that says, you can't do this with that type. And you stare at that and say, no, this type, that's exactly what I should be able to do with this type. And then you begin to realize, wait a minute, I suspect the compiler and I disagree on what that type should be. And I'm humble enough to admit that the compiler might be right, but the problem is I don't know what the compiler's thinking. What is this type? I thought T here should be blah, 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 and the compiler's saying, no, it's not that, it's something else. But I'm not sure what it thinks it is. So there's a couple of different ways three different ways I'm going to talk about how you can figure out what is the type of something. There's tools for that in the standard. There's a better tool in Boost, and then we can use the compiler to do this. So in the standard, we can include type info, and you can actually say, just say, I want type ID of x. Type ID of x is a structure that's returned, which has a function we can call called name, and it will actually return the name. That name might be helpful. And the reason I say that is there's a couple of issues. One is the standard says that it will not reflect whether it's const, volatile, or a reference. Well, in some cases, that's exactly what we're trying to figure out. I thought that this was a reference and it's not a reference, or I thought it was const and it's not const, something like that. So that's exactly what we might be looking for, and the standard doesn't tell us that. The other thing is that this is returning the mangled name. How many of you look at PK16 widget and tell me what is that type? Anybody an unmangler enough to tell me what that is? What? I think it's a pointer to a const widget, right? Const starts with a K, right? All right. So that may not be terribly helpful. So Boost has a better approach. Boost actually has, you include Boost type index.hpp, and what we can now do is we can say type ID with CVR, guessing what CVR is, the const, volatile, and references. The Boost is specifically saying we're going to capture that because you do want to know that. We're not going to throw that away. So it's telling us what is the type ID with CVR, and then the parameter is, or the function that we're going to call is pretty name. And what does that mean? That means it unmangles the name. That means it's not portable. There has to be a different implementation of this library for each platform, or for each set of name mangling rules. But that now will return the name for us, and it will return it correct with const, volatile, reference, and it won't have this cryptic name mangled name. But both of these techniques have another issue, another problem. What is that problem? I think Boost has solved most of the problems from the standards, but there's still an important problem that it's not solving. And what is that problem? That's right. If the reason you want to know the type is because you were getting a compile error, it might not be easy to run the program. Both of these require that the program be compilable and runnable. Right? So we can actually do this. So in this case, what we do is, and I want to give credit to Scott Myers. He's the one who kind of documented this, my first instance of it. And he basically said, look, we create this thing. In this case, I call it that type. And it's a declaration only. We don't know what's the implementation of that type. And then later on, we have a function that says name that type, where you pass in something. And all that does is it tries to instantiate a that type and what the parameter is. And the reason that this works is because when you say name that type of X, the compiler will tell you that it can't instantiate that type of char or that type of charref. Does that make sense? In other words, it's in the error message saying, this is the type, and I can't do anything with it. Why can't it do anything with it? Well, it's because we didn't define it for that type. We said, that type, if you ever want to use this, you need to have a definition, and we never defined it, so we're always going to get an error. But helpfully, the compilers tell you every time they give you the error, they said the error is for the template of that type of, and it tells you what the type is. Okay? So that is how we would be able to view a deduced type without actually being able to build. So these are some of the templates, or excuse me, the techniques that I consider them intermediate techniques. We didn't get into hardcore template metaprogramming, but these are the kinds of things that you're going to see as you start to play with templates over and over again. So I want to thank you very much. I think we're close to time, but I'm happy to take any questions. I can't quite see you, but I'm happy to take questions. Thank you very much.